Paul Jackson with PBT. You're watching the latest edition in our ongoing series of remote battery monitoring tips. Hello, and welcome to this installment of Battery Basics from Phoenix Broadband Technologies. Today I'm here with PBT's president, Joe Rocky, and we're going to be talking about the ideal versus the non-ideal elements of actually we've got one here, a lead acid battery. So what is an ideal battery, and is there really such a thing?
Paul, an ideal battery would be able to deliver an infinite amount of current for an infinite amount of time and occupy an infinitesimal amount of space and would work in any environment you subject it to. In reality, batteries are non-ideal. They can't supply infinite power.
Okay, so what are these non-ideal components and how do they affect the battery's life or performance?
Paul, a good way to describe this is to use the well-known Randles theoretical model of a battery cell. As we can see here, a cell can be thought of as a perfect voltage source in combination with several resistors that limit the amount of current the cell can supply. The cell voltage is determined by the electrochemical reaction between the metals used for the battery plates and the liquid electrolyte. Of course, it's a bit more complex than this, but this very basic model will serve to help us understand battery behavior. Our electrolyte in the diagram represents limitations of the non-ideal electrochemical voltage generator formed by the plates and the electrolyte. Discharging the cell causes our electrolyte to rise, and recharging the cell causes it to fall. The storage temperature of the cell also affects the value of our electrolyte. Our electrolyte will gradually increase as the cell ages, so measuring it can help us to predict the end of the cell's useful service life expectancy. Our metal is a fixed resistance associated with the metallic interconnections between cells in a battery. It doesn't vary or change with temperature, but it also limits the maximum current a cell can produce. In broad terms, our electrolyte and our metal are about equal in magnitude, and the combination of the two is what is commonly called the internal resistance of a cell. Our leakage is a very high resistance that causes a battery to self-discharge when not being charged. It's not measurable resistance, but including it in the model does help us to understand why batteries left uncharged for long periods of time will eventually lose all their charge. The capacitor C is very interesting. It represents the inertia in the electrochemical voltage generator, which causes it to react slowly to rapid changes in load current. C is a measurable parameter and typically runs about 1.5 farads per 100 amp hours of cell capacity.
What did you say a farad was again?
A farad is the expression of a device's ability to hold electrical charge.
Interesting. So that's the kind of the key word in the whole conversation. That's what you're measuring.
That's one of the parameters that we're measuring. We're measuring the capacitance of the battery in farads. We're measuring the individual resistances, which include the electrolyte, the metal, and the leakage. C also changes as a battery ages, and measuring it in combination with our electrolyte, which is commonly expressed as impedance or admittance testing, can indicate the overall state of health of the cell. All lead-acid batteries are subject to these limitations, and together these non-ideal battery components are limiting factors in the battery's ability to deliver power when needed. Continuously and accurately monitoring these changes, along with other important battery parameters, will help us to understand a great deal about the battery's health and to predict failures.
Thanks. Great information as always. For Phoenix Broadband, I'm Paul Jackson. Until next time, may the power be with you.